Ladies and gentlemen, I'd like to introduce the 5 Navy component speakers of our Lightning Talks.
Hello, everyone. Thank you for coming to my lightning talk titled Mass Spectrometry Advances for Energetic Syntheses and Environmental Analyses, which is based off of a number of projects that are ongoing in my research group. My name is Patrick Fedek, and I received my chemistry PhD from Purdue University and was sponsored by the Naval Air Warfare Center Weapons Division, where I'm currently working as a Phase 3 SMART Scholar. My research group focuses on a subset of mass spectrometry, specifically ambient ionization, which creates the ions that are analyzed by the mass spectrometer in the open environment outside of the instrument with no sample preparation or chromatographic separation. I'll briefly touch upon 3 intertwined projects with regards to the development of energetic materials. First is the developing a high-throughput reaction screening system for energetic reactions in the hopes of finding novel reaction pathways and alternative reactants. Second is utilizing mass spectrometry ionization sources to create confined volume droplets, which act as microreactors for the accelerated formation of desired energetics and precursors on a small scale. Finally, the third project is developing process analytical technologies through online reaction monitoring mass spectrometry for continuously tracking of energetic reactions. Traditionally, if you asked an organic chemist to describe the discovery process of novel molecules, it would be a cyclical process of having an idea of a new reaction, performing that reaction, working it up and purifying it, and finally, analytical analysis. Based on the analytical results, the organic chemist either tries to replicate the synthesis again, tries to optimize the reaction conditions, or has to change the reactant as a whole because they didn't work. My team are not organic chemists, so we do not fit that description at all. Instead, we are trying to take the lengthy reaction times and then clean up processes and remove them during the small-scale discovery process. And later, for larger-scale reactions, we are trying to improve the overall monitoring of the reaction. So rather than keep disrupting the process to take out a small sample to have us run analytical analyses, instead have the instrumentation in line with the system continuously providing data. Ultimately, all of these projects focus on trying to provide major cost savings to the Navy and the DoD through these high-throughput accelerated synthesis techniques and aid in the discovery of novel energetic materials in an expedited time frame, enabling improved lethality by shortening the development lifecycle of novel energetics. So like I said, we're not organic chemists. The first project, high-throughput screening, we utilize a low-cost automated pipetting robot, which cost about $6,000 from Opentrons, which can be seen in the top left. We adapted this robot, which is usually used for biological samples for PCR or sample preparation and dilutions, and we custom 3D printed a holder, seen in the bottom left in blue, to integrate our Teflon-coated glass slide, which is going to be our sampling substrates, to work with the robot. To deposit the various reactants and percentages of acid catalyst, we developed custom spotting protocols, which can be seen in the top middle. We can then place a number of reactants, such as the benzylamine and the glyaxol, which the structures can be seen in the top right, to form the Cl20 intermediate hexabenzahexaasa isowertane, HBIW, which for the next 3 slides will be the model system that we talk about. We can then vary the amine to screen other reactions that may form the cage structure, and we can vary the amount of acid that is utilized to catalyze the reaction. We can then screen these reactions with an ambient ionization source called desorption electrospray ionization, DESI, which can be seen in the center. The DESI source is built on a motorized stage and rasters across the spots on each row and ionizes the sample. While there are commercial DESI sources, the one we used is a low-cost home-built system. To ionize the samples, the DESI shoots charged solvent extraction droplets at the slide where the reaction mixture was spotted by the robot, and the reaction mixture is desorbed off the slide and flies towards the mass spectrometer. In the flight path, the reaction is trapped in combined droplets that are constantly shrinking, bringing the reactants together, and this forces the reactant to go towards product. In the bottom right shows a mass spectrometry analysis of a row of benzylamine and glyaxol and various concentrations of formic acid. If you look at the peak at mass to charge 709, which corresponds to the HBIW product, the intensity increases as less acid catalyst is added, showing that adding too much will actually hinder the reaction. The high-throughput nature of this experiment allows for rapid screening of a number of conditions at scales faster than solution phase chemistry. As mentioned, confined volume systems such as microdroplets, Leidenfrost droplets, or thin films are capable of accelerating chemical reactions. Acceleration occurs due to the evaporation of solvent, the increase in reactant concentration, and the higher surface to volume ratios, amongst other phenomena. While DESI droplets are combined volume reactors that spray directly into the mass spectrometer, which is ideal for rapid screening, to utilize this technology as a synthetic technique where we can collect material, we have been studying 5 other systems where collecting the final product is much simpler. Electrosonic spray ionization, ESSI, easy ambient sonic spray ionization, easy nano spray ionization are 3 potential spray-based methods on the left-hand side, where paper spray ionization is the thin film methodology. And finally, there are Leidenfrost droplets, which are not a mass spectrometry ionization source, but are still accelerate reactions. We explored the 5 of these confined volume methods to identify which reaction acceleration condition that might have the biggest impact on acceleration factors, including gas flow rate, reagent flow rate, voltage polarity, dry time for the thin films, stoichiometry ratios, and the substrate used for paper spray ionization. Compared to the bulk reactions, traditional round bottom solution phase chemistry, combined volume systems also reduce waste by screening reaction conditions in very small volumes prior to scaling up reactions to the bench scale. If you look at the overlaid spectra on the right-hand side, you can see after a 10-minute reaction, the peak at 709, which corresponds to the HBIW cage, is significantly larger for the Leidenfrost accelerated conditions compared to the bulk solution phase chemistry. So we started with microliter high throughput screening, then we saw confined volume droplets for small scale synthesis, which is on a few milliliter scale. And now we're moving towards hundreds to thousands of milliliters to look at large scale liquid phase reactions. In this work, there is no reaction acceleration, so we keep the ion source very close to the mass spectrometer inlet to prevent acceleration because we want to know what's going on in the round bottom flask at that exact moment in time. We developed an online reaction monitoring system that has a reaction in a round bottom flask. There's a pump that pulls the reaction mixture towards the binary T mixer. On the other side of the binary T mixer, there is a diluent and syringe pump to allow us to monitor higher concentration reactions in that round bottom flask, but not overload the mass spectrometer. The reaction mixture and the diluent are mixed in the binary mixer and then moved towards the continuous flow nanospray emitter and are sprayed into a portable or benchtop mass spectrometer. So sticking with the Glyaxol and benzylamine from the last few slides, we can track in real time the starting material benzylamine, and we see that the extracted ion chromatogram slopes downward at the very top at molecular weight 108 as the reactant is being used up. 2 intermediates grow in, and if we were to monitor the reaction longer, you would see that the ion at 473 would start to decline, such as it did in 237. And finally, we can see the steady increase of the HBIW molecule forming at 709. The reaction was monitored for about 900 minutes, but it only utilizes about 1 microliter per minute of reaction mixture. The goal of this project is to adapt this for novel reactions to track what intermediates are forming, are there any side products, and why are reactions potentially failing. So overall, SMART enabled me to focus on research rather than being a teaching assistant during graduate school, and it also allowed me through the internship portion to get a head start on my independent research career as I was already applying for grant funding from my laboratory prior to starting phase 2. SMART and working with NOC-WD has also enabled me to work with reactions and materials that many other academics or industry folk cannot, such as the energetic materials, or even access to some of our ranges for some of the environmental studies that we didn't have time to talk about today. This excellent jumpstart has enabled me to hit the ground running, and during my 1.5-year payback period, and now in phase 3, I was able to write 7 peer-reviewed manuscripts with a few more under review, present a number of conferences, and acquire a plethora of new research equipment shown below that has set off collaborations across the DoD.
Thank you, Patrick. Next, we have David Haig. His topic will be adaptive transmit waveform design for cognitive radar and sonar systems.
Okay, hello, my name is David Haig, and the title of my lightning talk is Adaptive Transmit Waveform Design for Cognitive Radar and Sonar Systems. Just a little bit about me. So my research focus is in radar and sonar signal processing. I received the PhD with a focus on acoustic signal processing from the University of Massachusetts, Dartmouth. My sponsoring facility is the Naval Undersea Warfare in Newport, Rhode Island. Now, my focus of research is particularly on transmit waveform design, the signal that a radar or sonar system transmits into the medium. And the idea behind it is that if we can adaptively design transmit waveforms to detect and localize targets of interest, we now have an adaptive capability. And this is loosely analogous to that of echolocating bats, which use a variety of echolocation calls to locate prey items in the midst of challenging noise and clutter in marine environments. And to sort of motivate this research a little bit, I wanted to show a figure, right, of a classic bat echolocation text that sort of demonstrates the change in bat echolocation calls throughout the detecting, localizing, and tracking stages of a bat while hunting for a prey item. Right, so the top panel is showing the bat at various stages of that process, and the bottom panel is showing the spectrograms, which shows the time frequency structure of the echolocation calls. The first thing you'll notice is that for the search phase, they're rather long duration, broadband type echolocation calls. They're good, they have a lot of energy, and they're good for detecting at range. Moreover, the time between those echolocation calls is relatively long. They're pinging and then listening. Now, as they detect a prey item of interest, they start to ping more often, and the time frequency structure of the echolocation call changes. It's shorter in duration, and starts to get a little more broadband. Once they have a fix on their prey item, they rapidly increase the rate at which they emit an echolocation call. The duration of those calls are also much shorter. And they continue this until they catch that prey item, and then the cycle repeats itself. So what we would like to do with radar and sonar systems is to have a similar type of adaptive method of changing not just the transmit waveform, but the type of processing and other aspects of the system. But the transmit waveform is really what gives us the most information about the target scene up front. And so we want an adaptive method, a method that allows us to transmit novel waveforms from time to time to extract the maximum amount of information about that target scene. That requires a waveform model that is adaptive in nature, but also has the necessary properties for efficient transmission on the real-world electronic devices that we use on these systems. And that led me to work on what's known as multi-tone sinusoidal frequency modulation. In short, the multi-tone SFM is a waveform model that possesses a discrete set of design parameters that we can adjust to synthesize waveforms with desirable characteristics. And the lone equation that I'm going to show you in this talk shows the actual time series of that waveform. It's simply stated a sinusoidal function whose argument is a superposition of sine harmonics weighted by these alpha sub k's. And those are the coefficients that we're going to adjust to synthesize waveforms with unique properties. Now, to date, research efforts have demonstrated that the multi-tone SFM is capable of finely tuning the waveform's characteristics by modifying these design parameters. I'll show you an example of that in a moment. But more importantly, these waveforms are transmitter friendly, and that the waveform's finely tuned properties are preserved when transmitted on practical electronic devices and as they propagate through the medium. So here's an example of what these waveforms look like. So in the upper left panel, I'm showing the spectrogram of an example multi-tone SFM waveform composed of 32 randomly initialized coefficients. What I'd point your attention to is that this is a smooth function that sweeps through a band, delta F, with very little transient-like artifacts. In fact, it's a very smooth spectrogram. And as a result of that, the resulting spectrum in the upper right panel concentrates the vast majority of the waveform's energy in that band with very little energy elsewhere. This is particularly important for radar systems. There's generally very strict FCC requirements, maintaining that you must keep the vast majority of the waveform energy in your band and very little mutual interference outside that band where you could interfere with other systems. As a comparison, I've also plotted the spectrum of an equivalent binary phase shift keying or BPSK waveform. You'll notice that that blue spectrum has very substantial spectral extent outside the operational band of frequencies. This is a common issue with these waveforms, and they require substantial signal conditioning to make them more spectrally compliant. As a result of this, their nice theoretical properties can sometimes be perturbed, resulting in re-optimization of the waveform afterwards. Now, in the lower left panel, I'm showing what's known as the ambiguity function. This is effectively the target response of this waveform. The x-axis represents time delay or target range, and the y-axis represents Doppler or target velocity. Now the energy is the color in that plot, and you'll notice that there is a concentration of energy near the origin. That's known as the main lobe. The rest of the bounded volume is spread evenly in the ranged upward plane, resulting in a pedestal of side lobes. And what this waveform is allowing us to do is that if in a target scenario, if we have multiple targets, the return echo signal is a superposition of them, scaled by their object size, delayed by the target's range, and shifted in frequency by the target's velocity. The resulting output of such a radar receiver would then be a superposition of the ambiguity function, scaled by the object size, delayed by the target's range, and shifted in frequency by the target's velocity. And what this thumbtack-like, what we call thumbtack-like ambiguity function allows us to do is to resolve closely spaced objects. The side lobes themselves determine our ability to distinguish a weak target in the presence of a much stronger one. And you get a nice picture of that pedestal of side lobes in the lower right plot, the correlation function, or the zero Doppler cut of the ambiguity function. Now, what we'll want to do with this waveform is modify its design coefficients to further refine its design characteristics. Here's how we do that. So in the left plot, I'm showing the result of an optimization problem that I ran on the waveform from the previous slide. So I'm trying to optimize the side lobe height over a specified region of time delays denoted by the red dashed lines. The optimization problem is reducing the area in that region while also placing a constraint on the main lobe width, which determines range resolution. The blue curve is the initial waveform from the previous slide. The black curve is the resulting optimized waveform correlation function. You'll notice that the side lobes are substantially reduced by a factor in some locations as much as 30 dB, or 3 orders of magnitude. This is all achieved while maintaining the range resolution, the same main lobe width of the correlation function. And you get a good picture of that in the right panel as I zoom in on the origin. And that's the idea behind this waveform model, is that it shows that you can modify these design coefficients and finely tune the waveform's characteristics. Now that's just one example that I've studied over the years. I'm listing a couple of publications that discuss other problems that I've studied using the multitone SFM waveform model. Feel free to reach out to me if you're interested in these or would like to discuss them in more detail. Before I conclude, I just wanted to say a few things about the impact that the SMART Scholarship has had on my career. First and foremost, my PhD studies were made possible by the SMART Scholarship. I probably would not have pursued these studies without the financial security that the SMART Scholarship provided. Almost as important is during my summer internships with my sponsoring facility, I had some great mentors, and they got me to attend several ONR program reviews of the Office of Naval Research, where I learned about the problems that my research could potentially solve for the Navy. This motivated or inspired my dissertation topic, and now I'm doing research on these very problems for those same ONR agencies. Now, in terms of notable achievements and highlights, I've already listed some of my journal papers and conference publications. The other thing that I'm really proud about is that I received a DoD award last year for my role in executing the littoral continuous active sonar experiments in collaboration with the NATO Center for Marine Research and Experimentation, or NATO CMR. This is where I had the opportunity to experimentally evaluate many of my waveform designs. And it's been a really rewarding and exciting experience for me. So with that, I'd like to conclude my lightning talk. Thanks for joining me. And if you have any questions or are interested in collaborating, feel free to reach out. Thank you very much.
Thank you, David. Next up, we have Shivan Parameswaran. His topic will be Aim Big, AI Model Blind Spot Investigation GIM.
All right. So my name is Shivan Parameswaran, and today I'll be talking about my project called Aim Big. It stands for AI Model Blind Spot Investigation GIM. I got a PhD in electrical engineering with a focus in image and video processing and AI and machine learning from University of California, San Diego. Currently, I work at Naval Information Warfare Center Pacific, NIVIC-PAC, with the Computer Vision Research Group. We are located in San Diego, California. So today, the project Aim Big is about developing a capability to stress test AI ML models so that we can uncover their weaknesses and blind spots so that they don't make these errors in the field. when deployed. So there is this, if you're in the field, you may have noticed in AI ML, the models can make really high confident errors. For example, if you show a picture of a cat and add some noise to it, you can make it get classified as an avocado or a monkey or something like that with really 99% confident. So when we have automated systems, these kinds of errors are really bad. And unfortunately, there is no way of testing these things today. So that is what this project is about and what we are trying to do. And why do we need that? So for DoD applications, and since I work for the Navy, we can think about a ship classification or detection system, an automated system. Now, we may be, one of our labs may be developing it, or we may be procuring it from a contractor. And we have these system with AI ML components, but we don't have a good way of testing them. They may show really good accuracy and on test data sets, lab data sets. However, in the field, we actually don't know what kind of errors it's going to show. In case of glint or cloudy day, have we dealt with really high seas and clutter in the background, right? So all these issues, we don't really know until we deploy. And if you face these errors in the field, it's really bad for the system, and obviously it's really catastrophic for our warfighters. So that is the point of Aim Big. We want to stress test, so that the model itself is part of the system. As you can see on the left here, we get a model, and we use this Aim Big framework to identify the blind spots or weaknesses in these models in the lab, right? And then we predict the images or the data sets that we will need to make these improvements so that we can improve the model before we deploy at the end. Why is this a problem? Because as I mentioned briefly, AI ML models are known to make very confident, blatant mistakes. So these images that I show on the right are images from recent years. So for example, a picture of a vulture, when you just turn it a little bit, is getting classified as an orangutan. Or a cat, if you change the contrast or the lighting, it gets classified as a candle or something else, right? So these misclassifications are great. It's okay, it's kind of funny to show for academic settings. However, in real world, these kinds of errors can be really bad. For example, automated driving. A stop sign, if it's classified as 40 miles an hour, it becomes a problem. Obviously, a gun detector, getting detected as a mousetrap, classified as a mousetrap, it's a problem. And for us, when we have ship classification or ship detection systems, we may end up seeing different qualities of images with different lightings based on the day. So a ship on the left, when shown with a little bit more brightness, they're getting classified as not a ship. With some occlusion, so the white part in the middle, right? With some occlusion, with some features occluded, it's getting classified as not a ship. So these kinds of errors are really bad, and it'll be really good for us as algorithm developers to find these out before we deploy it. And like I said, the worst part is that currently there are no methods that can uncover model blind spots. So the research focus of Aim Big is the following. Given an AI ML model, we want to develop algorithms to efficiently identify models' weaknesses. And we want to predict and generate data to perform model hardening in a mission-aware manner. So for example, one naive way of doing this is to test our algorithms on data with all kinds of different variations that one might think this model is going to encounter in the field. But that's not always practical. The situations change all the time. So this has to be done in a very adaptive manner. The second is predicting these data. What kind of data is going to make my model better? And doing this in a mission-aware or task-aware manner, because different tasks will have different properties and different challenges. Can we predict the data that'll make our model fit for a given mission or a given task? Why do we want to do this work right now? Because currently AI ML models are everywhere, and we are starting to use that in the commercial sector. But in order for us to start using it more widely in the DoD environments, we need a very good standardized methodology to evaluate these models. And using standard data sets for evaluation is not the most efficient and most trusted way to identify these weaknesses. What we want to do is, because collecting data sets with all the different kinds of variations, real data with all the different variations that one might encounter is impractical, in AIM Big, we leverage synthetic data to identify these shortcomings. To summarize the project, what is AIM Big? What is our goal? It's a collection of algorithms that will help us stress test AI ML models to avoid surprises in the field. And this is a step towards creating a standardized and shareable AI ML model testing protocols. It increases reproducibility, right? So there's an issue with reproducibility in AI ML domain right now. I can test it on my data set, and train it on my data sets, and then ship it to you, and the user will use it, but it may not show the same accuracies, probably because the pre-processing steps were wrong, the normalization of the data was wrong, right? So the reproducibility is a big issue. By creating a standardized protocol and a framework in order to do this, we can increase reproducibility. Not only that, it improves reliability and security. So a system, we can prove that our system is reliable in all these situations and all the different unknowns that someone will encounter in the field. And it's also secure because we can test it and understand the weaknesses so that we don't use a tool in the wrong situation. And by avoiding these pitfalls, we can promote trust in AI. So in general, our goal is to create better AIs. So as a smart scholar and receiving PhD in electrical engineering with a focus in computer vision and image processing, I was able to not only contribute as a researcher in the computer vision research team at NIVIC, but also start leading projects and lead the group. As part of the group, we have secured over $4 million since 2019 for assured AI ML projects. And this has also given me an opportunity to mentor smart scholars and other engineers at NIVIC. And as a PhD student, and also as a researcher now, I've served as a reviewer for top journals and conferences, which is very rewarding, and also gives anybody an opportunity to interact with the top researchers and top contributors in the field. So that's also, I attribute that to the Smart Scholarship and the opportunities that it has provided me. And thank you all for listening, and have a great rest of the symposium.
Thank you, Shebin. Next up, we have Joseph Fiordolino. His topic will be METCAL, Focused Modeling and Simulation.
Hi, my name is Joe Fiordolino. I'm a scientist at the Naval Surface Warfare Center in Corona. I'm a mathematician by trade. I studied at the University of Pittsburgh, focusing on numerical analysis and scientific computing. Today, I'm going to talk to you about a little bit of the work I do at Corona, which is on METCAL-focused modeling and simulation. So in essence, the work I do is I develop predictive modeling and simulation software for Navy applications. And I try to incorporate elements of uncertainty quantification, which are consistent with the Navy metrology and calibration program principles. Some of the applications we work on is directed energy, additive manufacturing, material sustainability and maintenance assessment, and there are others as well. I'll draw your attention to the left-hand side of the screen. The top, you can see an index or refraction variation near a ship. So we have a toy problem there with toy geometry kind of emulating a ship and looking at the variation in the index or refraction there with our own in-house built software. Below, you'll also see a diagram of an artificial neural network, and that's for high energy laser lethality. You input a beam, and then you look at what the lethality or what the beam looks like at the end of that. So that's a diagram, and we're both of these images we're planning on further developing the capability in the next fiscal years. Now, stepping into more particular item here is a subset of directed energy, which is the high energy laser propagation in atmosphere. Now, this is a very challenging area, namely because when you look through the planet, there's all different types of atmospheric composition. So if you're in a desert versus an ocean versus the tundra, the target set also differs too. Are you sort of firing towards the sky? Are you firing down towards the earth? Are you firing horizontally? All these kind of will factor into how much air or atmosphere you're propagating through. And the differences in the atmospheric composition and the turbulence will then affect the laser beam there in deleterious ways. One key factor there is the order of magnitude differences in length scales. For instance, the beam diameter is going to be on the order of fractions of a meter versus the length scales that you're propagating, which might be on the order of kilometers. So there's differences in items you need. Now, modeling and simulation software essentially aim to quantify the high energy laser system performance. So what you're looking at is how much energy are you getting on that target. So your laser lethality there. And you're looking for a real-time performance. So you want to know as you're firing or right before you're firing, whether that's a target that you could take out, how much time, because there might be multiple targets. And any gaps in knowledge, say for turbulence or thermal blooming, will then manifest in poor predictive performance than you might seek. So our in-house developed software kind of aims to fill in those knowledge gaps and support some emerging directed energy weapon system initiatives. The two codes we've developed are the Simulated Atmosphere for Beam Refractivity, also known as SABRE, and the Simulated Ensemble of Atmosphere Laser Interactions for Oceanic Engagement. So essentially what the SABRE does is it will simulate an atmosphere and it'll kick out an index of refractivity. And that index of refractivity you can feed into a laser propagation code to kind of look at the lethality. Whereas C-Line comes with the laser propagation code. So those are the two aspects for two different customers or two different scientific endeavors. Now, the modeling and simulation considerations we had to look into were essentially what were the canonical engagement scenarios. So we limit ourselves to ocean surface, small UAV with propagation lengths on the order of kilometers, sub 10 kilometers, and also laboratory channel propagation lengths on the order of meters. And the idea is that ultimately those will drive our other considerations on the physics involved as well. So for instance, we're looking at natural and forced convection, boundary layers, especially the near sea surface, and also kind of what are the tracers that ties into the atmospheric composition. And then the laser dynamics component of that as well. That physics involved, we now need to model, what are the equations we're looking at? How are we dealing with turbulence? In our case, the large eddy simulation. And then the refractive index models, and also essentially the paraxial equation coupling in there as well. And some getting into the Metcal principles there, we have that any instrument is going to have a measurement uncertainty associated with, so you don't know the precise values. Essentially, there's an uncertainty. And one way to kind of help with that is to compute ensembles. And from the ensembles, you can compute approximate statistics, such as the mean, variance, skewness, so forth. And those statistics can also help you in looking at the predictability of your simulations. And stepping forward, also the numerical methodology. So that will drive a lot of what you can do what kind of computer you need to do, sort of the speed of the algorithms, and how the algorithms might deal with geometry, essentially. And so there's a diverse number of considerations that must go into this. Some recent activities associated with this project are inclusion of additional tracer physics, that'll be your aerosol dynamics, lethality, looking at different models there, even documenting all this effort, this entire effort, which is quite an undertaking. And I sort of liken it to another PhD thesis. The other alternative models for index refraction or propagation equation, the efficiency and machine learning point of view, which I mentioned earlier, and even just the analysis, the mathematical analysis that is very nice to have and gives you a theorem proof of the value of the algorithms. And there's some open problems also alluded to, which is the near sea surface dynamics that are not well quantified, and also conversion from one of our high fidelity codes into those faster scaling law codes. As to how the SMART program helped me with my career, firstly, during my PhD studies, it freed up a lot of available time to actually work on and focus on my studies, my curricular studies, and also investigating any other topics that were not exactly aligned to the studies to kind of build up my capability moving forward. It also prepared me through the internships to hit the ground running when I actually arrived to my new job working as a scientist at the Navy. So the internships in particular kind of broadened my perspective of what was done in the Navy particularly, but the DoD broadly. And actually working here, you can see sort of there's just a very challenging set of problems that need to be dealt with. You have complex platforms and systems, engagement environments and geometries that I alluded to earlier. It's essentially wherever you look, there's a challenging problem to tackle. You get to interact and collaborate with world-class scientists and engineers. Kind of, if you look through your the Google Scholar or however you're reading literature, you see world-class cutting-edge research happening every day, but you also see that a lot of it's not in the public view. There's some very challenging problems that just are not reported on because they're of DoD importance and are guarded. So it's been pretty incredible and eye-opening being able to see that as a scientist for the Navy. Also, you get to travel through CONUS if that's something you enjoy. I've been to the NASA shuttle launch facility, White Sands. I've traveled to Redstone Arsenal, all over, supporting different missions and different in my work essentially. And also, there's patenting support as well. If you're into patents or you have good ideas, the Navy provides you with a lot of support. You don't have to pay anything essentially. You get to talk to lawyers or attorneys that can help you with the documentation, and that's been really helpful for me in particularly. Some of my achievements and highlights are publication, some on the way as well. The first publication was actually out of my internship, came out of my first internship there. Patents, some leadership opportunities. I've actually mentored ONR NREAP students and DoD SMART scholars as well, three on each case. And also a promotion to the acting head of a branch, the Metrology Research and Advancement Branch, which is our research arm for our department. And recently the Smart City grant as well to kind of further my studies and efforts towards validation of my software here developed.
Thank you, Joseph. Next up, we have Lillian Stewart. Her topic will be hydrodynamic behavior and safe performance parameters for submarine rescue assets.
Hi, everyone. My name's Lillian Stewart. I work in the Submarine Escape and Rescue Department. And I went to the University of New Hampshire, where I got my undergraduate degree in mechanical engineering, and I also got my master's degree in mechanical engineering. I now work at the Portsmouth Naval Shipyard up in Kittery, Maine, as a mechanical engineer. So the topic of the talk today is kind of in the area that I work, which is, like I said, the Submarine Escape and Rescue Department. And that's part of the Deep Submergent Systems programs. So basically, the Navy has two rescue vehicles, the Pressurized Rescue Module and the Submarine Rescue Chamber, or the PRM and the SRC. And you can kind of see them in the figure on the left. Basically, they're like mini submarines, which go down to sunken submarines in the event of an emergency and can attach to a sunken submarine and rescue sailors off and bring them safely to the surface. It's kind of like an underwater ambulance. So our job at the Portsmouth Naval Shipyard is to maintain these two rescue assets and also make sure our submarines and other countries' submarines are compatible with them. So if a submarine sinks, can we rescue people off of that submarine? My group in particular does a lot of structural analysis, and we work a lot with finite element analysis to ensure that we can complete these safe rescues. The topic for my talk today and kind of what my project was while I was interning at the shipyard and later came full time focuses on the hydrodynamic behavior and safe performance parameters for submarine rescue assets. So during one of my summer internships with SMART, I started working on a project that was focused on the actual interface between the rescue asset and the submarine itself. So on the right-hand side, you can see images of both the SRC and the PRM, and you can kind of see what that interface I'm talking about. Basically, the rescue asset goes down to a submarine, sits on one of their rescue seats or hatches, and attaches that way through a hydrostatic seal. So what I focused on was looking at the force balance between that hydrostatic seal and all the other forces working to break that seal at depth. So we're developing a tool, a mathematical tool, or a MathCAD file is what we used, which took real-time inputs like current, wave height, depth, and orientation, and was able to output whether or not a safe rescue was possible. So whether or not that seal would hold given all of those environmental inputs. So like I said, the first part of my project was to create this MathCAD tool and kind of this input-output sort of project. And like I said, it completed a force and moment balance, took the wave height, pressure inside the submarine, orientation, current, sea state, and it calculated drag force, hydrostatic forces, wave-induced inertial forces, umbilical loads to determine whether or not a safe mate, given all these conditions, was possible. So while I was working on this project, we realized that we didn't have drag coefficients for the submarine rescue chamber, and that's something we really needed in order to calculate the drag force given currents. So the second part of my project was to determine these drag coefficients for the SRC. So the first thing I did was created a 3D printed model of the SRC, a scaled model. And then I conducted wind tunnel testing at the University of New Hampshire using their in-house wind tunnel for various orientations and similar Reynolds numbers to what we'd see at depth. So this was a great way to bridge both the university and the shipyard and be able to use kind of what I had just learned in my fluids classes in this real world problem. So as far as the results and deliverables from this work, I created the 3D printed model of the SRC, which could be used in further studies, drag and add mass studies. We also created the calculation tool, which can be used in real life rescue events, given different environmental conditions, and determine whether or not a safe rescue can be made. We also provided and found supporting data for the SRC's smooth cylinder approximation to be able to have a range of drag coefficients given different Reynolds numbers for the SRC. And finally, I was able to help form a bridge between the shipyard and the university by having meetings with both my professors and my employees at the shipyard. As far as SMART's impact on my college and professional career, it's been really huge. I thought that the 2 summer internships I had at the shipyard were very important for my career. It was a great transition between academia and going into the professional world. And I was able to develop a lot of professional working relationships with my coworkers before I was just thrown into the full-time environment. I also was able to graduate early because of SMART, which let me fit in my master's program within just a couple semesters. And that was huge. So being able to graduate in a little over 4 years with a master's degree has been wonderful. As far as the SMART impact post-graduation, I've loved my job so far. I've had so many great experiences, gotten to travel to so many places, Seattle, Virginia, San Diego, and it's really expanded my view of what the Navy does and the great work they do. I had no idea about some of the technologies and different research done. I've also gotten to gain a lot of hands-on experience, both through surveys and different things like hatch training. That's been really important to me because I feel like a lot of my school career was just with books, and I've gotten a lot more hands-on. And finally, I've gotten to remain an active participant in STEM outreach while at the shipyard. I was really involved in college, and being able to continue that through different after-school groups and also programs like Naval Horizons has been really important to me. And I just wanted to say thank you to everyone who's watching and to everyone involved in the SMART Scholarship Program. I know it's really made a huge impact on my career, both through school and professionally, and I'm really grateful for all the experiences I've had.
Thank you, Lillian. Ladies and gentlemen, at this point, if you could navigate back to the agenda and click on the Q&A session, that will give you a Zoom link. Please follow that to get into our live Q&A session to listen to our 5 Navy component speakers.